So a random process is essentially a signal that's made up of random variables. Let's add a little bit more formality to that, and we can discuss some of the implications of what having a random signal means. For example, I guess as a teaser, when we think of random signals, we often think of noise, and noise indeed is typically a random signal. But random signals can have all sorts of different characteristics. The speech that you're hearing right now is a random signal. It's not completely deterministic. While it does have patterns in it that we recognize as words, there's also randomness to it. There's a little bit of background noise added, and the fact that if I say the same thing over and over, each time it will be somewhat different. And so we can view, in that sense, nearly every signal that we encounter in the real world will be a random signal. So here's an example of a random process. It's a sequence of random variables indexed by n. These random variables may or may not, depending on the index, of course, have the same PDF or CDF. So in the case of speech, the random variables making up my speech sequence will each have different PDFs as a function of time. An important distinction to make is a random process is not a sequence of samples of a single random variable. Now it may come down, we may have an instance where we actually do have a single random variable producing different values, and we put those into a sequence and we call it a random process. That could also be the same thing as a random process where we have individual random variables that are different, and they just happen to have the same PDF. And so we're going to stick with this. It's important for understanding what we can do and what we can't do with random variable or random processes, to understand exactly what it's made up of. So one example of a random process might be something like this. X of n is equal to let's call it y of n plus cosine omega n, where this is a random variable, and once you have a random variable in the mix, it in a sense corrupts everything else. They all become random variables as well, so now we have these two random variables. If, for example, if the expected value of yn equals 0 for every n, then we could find the expected value of x. It would be the expected value of the sum, which is the sum of the expected values, and since for any given value of n, the cosine of omega n is just a constant, that floats outside the expectations, and we get that this is simply equal to cosine omega n. So what might a signal like this look like? This could be a noisy cosine. So the reason for this example is to point out that at any given time, the expected value of x is different. So maybe this is x of 100, x of 250, and x of 325. Each of these will have its own PDF. So, once again, the way to think about a random process is not that it's a sequence of samples of a single random variable, but that there are many random variables and each one is producing a single output or a single sample. Are these values of a random variable always, are different values of a random variable always independent? And the answer is no. Also, they could have, so we could have a joint PDF that expresses each of these, and that joint PDF could be quite large. If you have something that's an infinitely long random process, it then has an infinite number of random variables, and they may be all related to each other, which means we now have a PDF that is also infinite dimensional. Okay, now that we've described some of those parameters, let's see what happens when we take expectations and when we relax some of the things that I've just described. The first, what is the mean of a random variable? Well, as shown up above here, the mean of a random variable, the mean of a random process is in general a function of the index. So the mean of x of n is going to be in general a function of n. We have the same type of thing with autocorrelation, and I guess I haven't brought up autocorrelation. We've talked about correlation and covariance, but not autocorrelation. So autocorrelation is, once again, just like correlation, but we use the term autocorrelation when we're talking about random variables within the same sequence. So instead of the correlation between x and y, we now have the correlation between x at in time n and x at time m. And we give that special notation. We call that x, or rxx n comma m. Now, so far we've assumed implicitly that everything we've been doing is with real output random variables. They could just as easily be complex. So if we have complex random variables, we take the conjugate. If RVs are complex, we take the conjugate of the second term. So usually we're dealing with real random variables. We don't have to worry about it, but occasionally complex ones will come in, especially if you're dealing in communications. Or if we're looking at spectral values, for example, that have magnitude and phase, we may have complex values that we need to keep track of. Okay, so we've now established that we have functions of time for our mean and for our autocorrelation. Sometimes in real life, actually almost always in real life, we do not have the PDF to work from. So finding the expectation is going to be really difficult. In fact, the only way that we can do it in such a case is to try to approximate it numerically. But how do we do that? Well, back to this example here, of our random process that's essentially a cosine function plus noise, if we could regenerate that an infinite number of times or some large number of times and average all those waveforms together, then we could come up with the mean, and hopefully the noise would average out and we would be left with just our cosine value. So that's great, but in practice, if we're dealing with a physical quantity, starting over from scratch and generating it again becomes very, very difficult. In some situations, for example, we were doing some work with medical signals, and often they're periodic as a function of, say, the heartbeat or respiratory rate and so on. We could take the same part of the signal from our heartbeat signal over many iterations and line them all up and average them and get what looks like a much cleaner version of the signal that we're looking at. We are doing a lot of assumptions when we do that type of thing. But let's step back and find out when we can legitimately estimate an expectation on a random sequence. So we're going to introduce this concept of ensemble average. So this will be what I was just trying to paint a word picture of earlier when we were averaging many realizations of this noisy cosine, or we're averaging many realizations of a heartbeat, maybe single heartbeat signal taken multiple times to get an average or prototypical heartbeat signal or this cosine. So an ensemble average is in general or often impossible to do. So if we were to go back to our previous example here where we have x of n is equal to y of n plus cosine of omega n, we would find the average at time n naught to be I equals 1 to n. In this case, we would have y, and I'm going to put a superscript here, to indicate that it's another sample or another realization of that random variable, and then our cosine of omega n naught. So if such a quantity is within our realm to achieve, then this will work. The important thing to remember here is that we will get a different value, or may get a different value, and in this particular case, most likely will, value for each n naught. Okay. So the next concept is stationarity. And with stationarity, we come away from this difficult property of having to have multiple realizations of the same thing. In reality, back to the heartbeat example, if we somehow had an infinite number of parallel universes and we could measure at a particular time the heartbeat of the same person across all these parallel universes for the same period and then average all of them together, that would be an ensemble average. Such things only exist in Marvel movies and other weird science fiction things. So let's go back to look at stationarity. If the statistics of the random variables in a random process do not change as a function of n, then x of n is stationary. Or we say that x of n is stationary. So when I talk about statistics, what does that mean? In general, you could say the cumulative density function, or the PDF. So this becomes really nice. Stationary processes, I guess, are very rare in reality, but so are linear systems, and that doesn't stop engineers from approximating nonlinear systems as linear systems and going along merrily and happily on their way. So we're going to do the same thing. We will, for example, assume that speech is stationary, at least for 20 to 40 milliseconds. Or the other signals are stationary, such as the air conditioning noise that you might pick up in a room, which may be stationary at least until the air conditioner turns off. But we assume that's good enough, and we proceed because it's a very powerful tool. So if we have stationarity, then our autocorrelation and our mean functions are simplified quite a bit. So for autocorrelation, it turns out that we've defined it above the autocorrelation as a function of n and m. Well, the absolute position shouldn't matter anymore, because since the PDF doesn't change, it won't change between time n and time m and time n minus m. What would matter would be the separation between those two random variables, and so we can simplify the autocorrelation n comma m as the autocorrelation of n minus m comma 0, and then we simplify that as just a function of the difference, or the separation between those two. So we're going to now write autocorrelation in terms of a single variable, where this is the separation. I should have written that differently. That should have been an n. There we go. Likewise, our mean and variance are constant with respect to n. Like so. Okay, so stationary is fantastic. Recall, what makes something stationary? A random process is stationary if every random variable, or in other words, the random variable at every time index, has exactly the same CDF. So this is a powerful tool, but it's hard to use it. In theory, it makes a lot of sense. But in practice, how are you going to know what the CDF is for a particular sample when you're measuring a signal? Let's make it real. We take a microphone and a little recorder, and we go and we measure what seems like a very stationary signal, fan noise or something like this. It's pretty white. So we're measuring this sound, and we want to know, is it stationary? Well, to know if it's stationary, we would have to look at each sample that we've collected in our recorder, and we would have to know what the cumulative density function or the probability density function is for that sample. Well, all we have is a single sample. How are we going to know? Well, we can postulate that it's the same, but we don't know. At this point, we're guessing. So we need something a little bit more useful, and that something is this idea of wide sense stationarity. So a random process is wide sense stationary if the mean and the variance do not change with time. Well, this is a lot easier to estimate from observations. Variance, another way of saying that is mean or autocorrelation. Could be inserted in there as well. Okay, so if a signal is wide sense stationary, then a lot of the properties that we're after still hold. A signal could actually be wide sense stationary and not be stationary, but the wide sense stationarity will be quite useful for us. Another last concept that I'd like to cover in this lecture is this idea of ergodicity. For an ergodic process, the true mean and variance may be approximated via sample averaging. So we now get to the formulas that are kind of intuitive for us. That is, the mean we would expect to be just the sum over a number of temporal samples. So for an ergodic process, this works for sufficiently large values of L. Likewise, we can estimate the variance and we might come back and talk about this. Some of you may have run across the sample variance versus which has an L-1 there instead. One leads to a bias and the other leads to a lower variance estimate. We'll talk about that later perhaps. But finally, we can do the autocorrelation function in the same way. And I'm putting in the conjugate in there because when we do conjugate values, autocorrelation, we sometimes do want to know what it would be for complex values. The variance, we use the absolute value. We get a real value on the output. And mean, of course, could be complex or it could be real, and it doesn't make a difference with the equation. So ergodic processes, if we have a wide sense stationary process, then for anything that we're going to run across, it'll be ergodic.